All right. The next slide is just called It's All About ACC. So we're going to talk about how we regulate the activity of acetyl-CoA carboxylase. And we're going to talk about how this whole system is differentially regulated whether we are in a need state or a fed state. So on this first slide, we're going to talk about what happens if we are in a need state. And the need state is kind of highlighted by everything that we have in red on the picture. Okay, so I'm going to sort of walk through it on the picture first, and then we'll take a moment to sort of write it out. But I want to highlight first where we're going to start in this picture is all the way down at the bottom here. Okay, and it starts with a process where we have a cyclic AMP dependent phosphorylation. So hopefully it's not a stretch for you guys to recognize that is happening with pKa. So what I'm going to highlight first on this picture is where things are happening sort of with our need state. Okay, so and then we'll kind of go through and sort of talk about what's happening. So I'm going to draw sort of a picture here, and I'm going to break it apart into two pieces because we sort of do have two arms that are happening depending on whether we are talking about global or sort of local use here. And then we also need to think about how we're differentiating based on cytosol versus mitochondria. So I'm going to start all the way down here at the bottom. We'll look at this picture first, and then we'll put that picture into words. Okay, so need state. If we're in a need state, pKa is going to be active. If pKa is active, it's going to be phosphorylating things. So in this case, we are going to have a hormone-sensitive lipase that is going to be taking triglycerides that are stored in adipocytes, converting them into fatty acids, which then can be exported into the bloodstream. Remembering, fatty acids are transported as a fatty acid albumin complex. Okay, if we are a cell that is in need, and specifically here we're going to be talking about liver cells because there's the aspect for the liver to do two potential things with acetyl-CoA that we get from beta oxidation. But we get fatty acids that are sitting now in the cytosol. And remember, we talked about in our activation and transport video that fatty acids don't have great functional groups. So what we need to do is we need to activate it. And that requires us putting on that CoA hat. So we're going to generate fatty acyl CoA molecules, okay? And then we do a little bit of swapping with the hat that we have on there. We're going to put on a carnitine hat so we can get through our carnitine transporter. Then we get back into now the mitochondria, and we're going to put our old blue derby hat back on, and now we've got a fatty acyl CoA that is in the mitochondria. Remember, we said that is the rate controlling step for beta oxidation. If fatty acyl CoAs got into the mitochondria, they are going to be broken down by beta oxidation. We talked a lot about beta oxidation. 4 steps: oxidation, hydration, oxidation, cleavage. Okay, and so every one of these lines oftentimes represents a metabolic pathway that we've studied in detail. So make sure that you can look at any of these lines and sort of understand what's happening in that process. Beta oxidation endpoint is acetyl-CoA. So what we do with acetyl-CoA here depends on whether we are looking at the use of that acetyl-CoA globally or locally. Remembering, this is in a hepatocyte, this is a liver cell. So the liver cell might need its own energy. So in that case, it's going to take acetyl-CoA. It's going to be taking it through the citric acid cycle, right? The first step is to generate citrate. That citrate continues on in the citric acid cycle and is going to generate ATP by going through electron transport and oxidative phosphorylation. Again, local use by that liver cell of the lipid-derived acetyl-CoA. Another thing that the liver can do is it can say, you know what? I need to help out the rest of the body. I'm going to take some of that acetyl-CoA and going to make it into ketone bodies. We're going to talk a little bit about ketone body synthesis when we talk about cholesterol biosynthesis, since there's a common intermediate there. But these ketone bodies can then be exported for global use. Okay, so all of these pieces we've kind of talked about, looking at them on this picture here. Now we're going to sort of talk about and put it all in words over here. So when we talk about what's going on here, we are going to begin with pKa phosphorylation. Right? That's our R2C2 enzyme, right? And if we are in a need state, that means we are again in a phospho state. Okay, so that's going to be pKa sort of being activated by having cyclic AMP that's produced by adenylate cyclase. Again, remember all of those pieces, but we're going to have pKa phosphorylation. I should say that's probably better to say pKa activation. Okay, pKa is going to do phosphorylation, but really our cascade begins with the activation. Smaller eraser, pKa activation. And again, that's with that R2C2 enzyme that now is going to become free catalytic domains because those regulatory subdomains are going to be binding cyclic AMP. So now that pKa is active, what it's going to be doing is it's going to be phosphorylating that hormone-sensitive lipase. So hormone-sensitive lipase. Okay, that's going to mobilize fatty acids to circulation. So mobilize fatty acids to circulation. And again, they're going to complex with albumin to do that. Okay. And then once we've got fatty acids inside the cells, then we're going to need to do that activation and transport. So once the fatty acids are inside the cells, specifically those fatty acids are going to be in the cytosol. Okay, 2 steps need to happen. We need to have activation, okay, which means we are going to attach it to CoA, which was our blue derby hat. And then we're going to need to transport into the mitochondria. So a transport to the mitochondria. I'm just going to make our little red hat there reminding us that we need to use that carnitine transporter. Okay, and then we're going to be inside the mitochondria. Okay, once we are inside the mitochondria, this is sort of the rate determining sort of step. So once we have fatty acyl-CoA in the mitochondria, that is the rate determining step for beta oxidation. Cells are then going to go through beta oxidation, which remember is that oxidation, hydration, oxidation, cleavage. Okay, endpoint is acetyl-CoA. What we do with acetyl-CoA, if we are in a liver cell and a hepatocyte, is going to depend on whether that acetyl-CoA is going to be used locally or globally. Okay, so if we used it locally, that means it's going to be going through the citric acid cycle, electron transport, oxidative phosphorylation, ultimately to make ATP. And then global use means that acetyl-CoA is going to be used to produce ketone bodies, which again are then going to be exported to the bloodstream. So one last little piece to sort of highlight here is that we've been talking about what sort of is happening in our need state and how the rate determining step for beta oxidation, which is what's going to be happening with fatty acids in a need state, is getting those fatty acids into the mitochondria. But what's really important to highlight is that we also need to make sure that we are inhibiting ACC. Okay, so a big part of what we need to do here is we must be inhibiting ACC. I'm going to zoom in here and just kind of highlight. Here is the ACC enzyme. Now, we haven't talked about the ACC enzyme in our need state because the ACC enzyme is the rate controlling enzyme for fatty acid synthesis. But it should make sense that we need to make sure that that enzyme is not active when we are in a need state. And what we can see here is that enzyme is inhibited by both AMP and then a cyclic AMP dependent phosphorylation. So again, we are going to have pKa making sure to inhibit ACC. So it's going to make sure that we are not doing fat synthesis if we are in a need state. All right, so that's the details for what happens in a need state. Same picture, different story here for what's going to be happening if we are in a fed state. Okay, so fed state, different color. I'm going to be talking about blue. I'm going to do the same thing. We're going to walk first through sort of what's happening on our picture, and then we'll put stuff with our picture into words. So here's where we need to start with this story, as we're going to start here. Okay, we are going to start with excess acetyl-CoA. We're going to go through these details in a minute, but let me circle sort of first what's happening. Excess acetyl-CoA, we're going to be all the way over here, sort of on this arm. Okay, all of these pieces. So that's what we're going to be talking about here. So let's zoom in here and sort of talk about what we have here. So if we have excess acetyl-CoA, and we'll highlight again when we write this stuff down, this excess acetyl-CoA is derived from excess carbohydrate or excess protein, excess amino acid that's broken down. This is not excess acetyl-CoA that we have from beta oxidation, because if we are doing beta oxidation, we're in a need state. So we do not want to be taking that acetyl-CoA and making it back into fatty acids. So this is only from carbohydrates or amino acids. Okay, so what's going to happen is that acetyl-CoA is going to be combined with oxaloacetate using the enzyme citrate synthase. Now, this is an important piece. If we are using this as a way to do fat synthesis, that citrate needs to be exported out to the cytosol. Okay, so we're going to have our tricarboxylate shuttle. So tricarboxylate shuttle. Okay, if we're going to be doing that, that means that citrate can't be sucked into the citric acid cycle. So a hypothesis would be that we don't want citrate synthase to be associated with citric acid cycle enzymes, because it needs to be allowing its metabolite to exit the mitochondrion. So again, that's what we're going to have. Citrate is going to exit the mitochondrion through our tricarboxylate shuttle, and now we're going to have citrate out in the cytosol. Okay, this is where the enzyme citrate lyase, now we don't have, again, we talked about this, we do have malate dehydrogenase as both cytosolic and mitochondrial isoforms. We do not have a cytosolic isoform of citrate synthase. So we can't take citrate synthase that lives in the cytosol and reverse this reaction. But what we do have is an enzyme that does do it. It's called citrate lyase. So citrate lyase is going to take and break apart citrate essentially into acetyl-CoA. I'm going to highlight here that we do regenerate oxaloacetate that's then going to return back into the mitochondria by the malate aspartate shuttle. Now we're going to have acetyl-CoA that is now excess acetyl-CoA that's out in the cytosol. Okay, this is where the acetyl-CoA carboxylase chemistry happens. Remembering that chemistry basically is going to be taking acetyl-CoA. We're going to need to burn some money, grab bicarbonate as a carbon source. We're going to be essentially adding CO2 because we're doing that chemistry by having transferable CO2. We need vitamin B7 for that. Okay, another video talks about ACC chemistry, but adding CO2 onto acetyl-CoA generates malonyl-CoA. We went into pretty good detail on the biochemistry that happens with fatty acid synthase machinery. Okay, we've got 7 sort of enzyme domains that we have in fatty acid synthase. So doing all that chemistry to basically zip together the net equivalent of zipping together acetyl-CoA molecules. Now, that happens because we essentially are going to have acetyl-CoA as an electrophile, malonyl-CoA as a nucleophile. That's how we're going to be doing that carbon-carbon coupling. We generate then a saturated palmitate molecule. So palmitate is 16 carbon atoms, fully saturated. So if you need to do some modifications, maybe you need to make it longer, maybe you need to add some units of unsaturation. Lots of biochemistry there. All I asked you to learn about was the fact that if you need to make it longer, you're going to use elongases. If you're going to add some units of unsaturation, you're going to use desaturases. Okay? At the end of the day then too, you're going to add DHAP to it. DHAP is the 3-carbon molecule that we can siphon off of glycolysis. That's going to provide our glycerol backbone. We're going to put our fatty acids onto it, and we are going to have a triglyceride. That triglyceride is going to be exported from the liver as a VLDL particle. Remember, that is going to have the ApoB100 protein on it. That provides stability and provides directions. The directions tell it to go away to the liver and out to peripheral tissues. If it's gone out to the peripheral tissues and everyone's like, nope, I'm good, totally fine, fed state, you go take that where you need to take it, what's going to happen is it's going to take it to fat storage. We've got a little bit of transport chemistry that has to happen in order to get those fatty acids into our adipocytes, reassemble them, should show the arrow going this way, reassemble them into triglycerides, and now we're storing those lipids. Wow, I know that was a lot. One more thing to kind of show you on the picture before we sort of put this into some words and sort of write down and summarize this is, again, to make sure we don't have a futile cycle. We do not want to be taking fatty acids that we're synthesizing in the cytosol from fatty acid synthase because we're in a fed state and allowing them to go into the mitochondrion. So look what happens here. If we are producing malonyl-CoA in the cytosol, this is going to inhibit that carnitine transporter, okay? It's important that we don't take fatty acids that are derived from the anabolic fatty acid synthase process and allow them to be catabolically transported into the mitochondrion so they can be broken down. Wow, I know this is a lot. So let's take and just kind of summarize that in words. We're going to talk about this over here once I sort of start writing things, but to just sort of highlight what we have here. In my iPad, there we go. Did not want to zoom out. Let's just kind of highlight right here, ACC, right? Fed state, we want to make sure that ACC is doing its chemistry. So look what's happening here. When we were in a need state, it was inhibited by pKa. Now we've got a phosphatase, okay? We've got an insulin-dependent dephosphorylation. So dephosphostate, we're going to have fed state. Insulin dependent. So when insulin levels are high, we're in a fed state. That's going to be activating ACC. That's going to be putting us into that fat storage mode. Again, highlighting why it's a problem if you have elevated levels of insulin. You're constantly putting your body into that, hey, let's synthesize fats for storage sort of scenario. All right, so we went through our picture. So let's wrap up here by putting all of this into words and sort of summarizing it. Okay, so where we begin is we're going to begin with excess acetyl-CoA. It's very important to highlight. Again, this is excess acetyl-CoA in the mitochondrion. This is going to be from carbohydrates, okay, or amino acids. We are not going to have this from fatty acids. If you have broken down fatty acids into acetyl-CoA, you are not going to be then exporting that out to have it remade into fatty acids, okay? Highlighting too, this is controlled by insulin because insulin is going to be controlling and putting us in that dephosphostate, okay? So that dephosphostate, okay, is going to be what's going to activate ACC. So all of this is internally consistent. Fed state means dephosphostate. Fed state means high insulin levels. High insulin levels are going to activate a phosphatase that is going to dephosphorylate and thus activate ACC. Okay, so let's walk through what's happening here. We are going to be having acetyl-CoA. Again, that is excess and in the mitochondria. Okay, we are going to be combining that with oxaloacetate, and we are going to be having citrate synthase convert that into citrate in the mitochondria. We are going to be using the tricarboxylate shuttle. So tricarboxylate shuttle to get citrate now out in the cytosol. Okay? And then we're going to have citrate lyase, making it back into oxaloacetate, and then now acetyl-CoA, still in excess, but now in the cytosol. Putting this last piece together, that oxaloacetate that's now in the cytosol can return to the mitochondrion using the malate shuttle. Okay? So we are now going to be having some acetyl-CoA because ACC is active, okay? And that's happening because we are having insulin is going to be activating it. It's going to be taking some acetyl-CoA and making it into malonyl-CoA. Malonyl-CoA is going to be our nucleophile. Acetyl-CoA is going to be our electrophile in fatty acid synthase chemistry. So we're going to have fatty acid synthase chemistry. A couple of great videos sort of talking about the chemistry that happens with fatty acid synthase. But the end of fatty acid synthase chemistry is you're going to get a C16 saturated fatty acid, right? That's what palmitate is. Okay? You can have chemistry with elongases. If you want to make it longer than C16, you can have chemistry that happens with desaturases. If you want to have it have any units of unsaturation, but you're going to be putting this onto our glycerol backbone. That glycerol backbone is going to be coming from DHAP. Okay? These come together and then make our triglycerides. Those are going to be exported as VLDL particles, reminding ourselves that those VLDL particles are going to have our ApoB 100, and that is going to be the directions that allows it to go to other tissues if they wanted to have a go at it, but ultimately we're going to be going to adipose tissue for storage. Okay? The last little piece here, again, it's really important to think about these complementary sort of pathways, making sure that they're not happening at the same time because that would be a futile cycle. One important piece is that malonyl-CoA, and we haven't talked about the mechanism or how it happens, but I do want you to know that malonyl-CoA is going to inhibit that carnitine transporter because it is really important to make sure that fatty acids that we make in the cytosol are not allowed to go through that carnitine transporter and get into the mitochondria. Because if we've got a fatty acid that went through the carnitine transporter and found its way into the mitochondrion, it's beyond the point of being able to regulate or control. It is going to be broken down by beta oxidation. Okay? So a lot to think about there, but it's all about whether or not ACC is active and ultimately about whether or not fatty acids are allowed to go into the mitochondrion.